Hello, everyone. My name is Sarah Alden. I will be starting off our presentation as I am the project manager for this week. For this project, our team was tasked with designing a 36-foot aluminum research vessel for Texas Parks and Wildlife. And the goal here was really to find a boat configuration that was not only affordable but practical, something that was able to handle marine research tasks while also staying within budget. On the next slide, you will see that our team was made out of 6 people: myself, Abdurrafi, Daniel, Logan, Praneeth, and Reagan. And we each had responsibilities based on our areas of strength. Each person focused on different systems of the vessel, which really helped us stay efficient and organized throughout the project. And I will pass it on to Reagan to introduce our project.
All right, so we're going to go over what are the general outline of what we're trying to do with our project. So on the next slide, go into our executive summary. We're looking into the Texas Park and Wildlife Marine Research Vessel. We're trying to get something that's both efficient and cost effective. The considerations we're going to be looking at are going to be the construction cost, operating cost, ease of maintenance, speed, durability, and operating space. And the methodology we're going to use to select the vessel is going to be the constrained weighted factor model. So if we look on the next slide, we're going to go through what that means. As we look through our methodology, we got the applied constraints is going to be a 0-1 multiplier for all the design factors. We're going to assign the 1 if it passes the criteria. Then on our second step, we're going to score each vessel from 1 to 10 for all of the factors. Step 3 is going to be to multiply each score by its own weight. So as we see here, we get the final score for each one of our configurations is the constraint times the weight times the factor score for that particular vessel. And then we will select the vessel that has scores the highest. So we ended up going with a 36-foot aluminum boat with a single diesel engine and a full cabin, which was configuration number 15. So this will be strong enough to handle the weather. It'll have enough space for the crew to operate appropriately. And we're going to balance the cost and the maintenance for the Texas Park and Wildlife. So go to the next part of the project.
So the second part of the project was organizational structure. If we go to the next slide, we'll see that we talked about 2 different types of organizational structure. One being the initial structure to meet the immediate needs of the project. And so we decided to structure that as a pure project organizational structure, where every sub-team is poured into a single project only. And each one divvies time up to that singular project. If we go to the next slide, we'll see what the planned future organizational structure would be for down the road needs and additional projects. In this case, we decided upon a matrix structure in which each team commits a certain amount of labor hours to individual projects, multiple individual projects, depending on their needs. So then we moved into the next part of the project, which I will pass off to the bill of materials.
All right, so on the next slide, you will see that our approach to building the bill of materials really started with dividing responsibilities by system. And here each team member really took ownership of their assigned areas, and this helped us stay focused and pretty efficient. We prioritized components that were marine grade, reliable, and available online. We also made sure that everything we picked was compatible with our chosen vessel and realistic to install based on the layout. And for every system, we just looked at cost, quality, and performance, and we made decisions that really balanced all 3. As we really finalized each section, we reviewed the full BOM together to make sure that the total cost stayed within budget and that the parts would all work together as a complete vessel. And on the next slide, we can see that this is an overview of our total BOM costs, which came to a little over $102,000. The propulsion system was what made up the biggest share at 38%, mostly because of the cost of the diesel engine, the propeller, and the fuel components. The hull and the electrical systems followed pretty closely since those also include structural materials, wiring, lighting, power systems. And then the navigation, anchoring, and research systems made up around 18% total. And even though these are smaller categories, they do have some essential equipment like the radar, the steering controls, anchoring hardware, and the crane. And these all support the boat's functionality during these research missions. And overall, we were intentional about staying within budget while still building out a complete practical vessel. So I'm going to pass it on to the next section.
So now we then moved on to project planning. We initially spoke about the work breakdown structure, linear responsibility chart, and Gantt chart. The purpose of developing these tools, especially the work breakdown structure, is to subdivide the system level activities into work packages. So we were able to identify the major systems used in our bill of materials and then subdivided them into detailed work packages where we could assign them to personnel responsible for the project. And with regards to the linear responsibility charge, the purpose is to assign responsibility of those work packages identified in the work breakdown structure to the personnel responsible. And the Gantt charts to estimate the timeline for activities identified, work packages identified in the work breakdown structure. So for more detail on how we prepared our linear responsibility chart, we assigned a responsibility consistent with the initial organizational structure due to the fact that the team members were going to be only focusing on the project. So this organizational structure was the pure project organizational structure. And for the linear responsibility, how we assign the responsibility of the task was to use the code system where we have one letter code to assign responsibility, as we can see in the chart. And these codes were categorized into four levels: primary responsibility, secondary responsibility, approval, and review. Moving on to the Gantt charts, this was essentially developed to estimate the timelines. And how we did that was we settled on using weekly intervals for tracking so as to give us as much detail as possible without overwhelming the schedule, rather than using days, which will give even more detail, but you have too much information that won't be useful. So in determining, we can see on the Gantt charts that there are several task dependencies, and we identified them by looking out for the flow of the project. So the tasks and the resources that are required to be complete before the next activity begins. And in the case where there are delays in dependent activities, it results in the delay of the entire project if those activities are on the critical path. So in how we envisioned we were going to manage those potential delays was we were going to reprioritize our resources in order to get the project back on track. So moving on to the next slide, the budget.
For our project budget, we've organized it on into three main parts. Next slide, please. Next slide, please. For for the labor cost, which covers all workers on the project, then it comes the material cost, including key component like the hull, propulsion, and electrical system, and indirect costs, which is our fixed monthly expenses. From the beginning, our goal was to manage these costs carefully and keep the total spending under $750,000. We say focusing on that goal while keeping the project on the track. In the next slide, we can see that our our total budget cost us only like $669,784, which the biggest spending happened in the second month, mostly due to high labor and supply costs during a busy phase of the project. After that, the costs started to drop as we completed the major work. We finished the project successfully and stayed well under the budget which shows that our planning and spending were well managed through. And then we can go to our next phase of the.
All right, so now we're going to look at the project network of the overall activities that make up the completion of our project. So on the next slide, we're going to be looking here. These are the activities we've highlighted to be super important. We don't want to have every task, obviously, for brevity. So we have everything from the project planning all the way to the end where the sea trials are. So we have an optimistic, a likely, and a pessimistic category. This is set in days. And to calculate the expected time, we use the formula at the bottom. And the same with the variance for each one of these activities. So that we then put them into a network. So going on to the next slide. Here we have our critical path on our actual network diagram. Each square is going to be one of those activities. It's going to have the early start, late finish, early finish, and then that expected time and variance is going to be in the middle. And the red line going through is going to be what our actual critical path is. This is where 0 slack is in the production of this vessel. And so we can see that the critical time for this to be completed is going to be 264 days.
So here, yeah, we have moved on to the crashing, which basically refers to the process of shortening the project duration by allocating the additional resources. So this typically happens at an expense of an increased cost. This is often done when there is a pressure to meet the deadlines. So the project was originally set up to a span of 20 weeks, but we have crashed that to the 17 weeks. This resulted in a total increase of $77,600, pushing the budget to $8,03,000. So the labor costs also increased by $18,700 due to the compressed timelines. The hiring costs increased by $16,000, which was spent on bringing in extra help for the key tasks. And then the firing costs increased by $24,095, which were incurred due to the increase to release the staff early or reorganize the workforce. So the key takeaway from this is crashing demonstrates a trade-off. While the project duration was reduced, the overall cost exceeded the initial budget. Next slide. So here we have discussed about the crash network, where we have calculated the labor cost incurred in each activity, like all three types of workers, that is professional, skilled, and unskilled. So the labor cost before the crashing was $1,92,320, while that of crashed after that is like $2,01,020. The difference between the crashed and the labor budget is around $18,700. So let's move on to the next slide.
So another methodology that we used to smooth out the project was leveling. And we go to the next slide. And the goal of leveling was to smooth out the labor demands. So in the original project, it was fairly spread out as to the needs for labor. And so the goal of leveling was to smooth it out such that hiring and firing costs would be reduced across the board by utilizing the same labor over again. And as you can see in this slide, and we'll go to the next slide, leveling the labor and concentrating it more towards the middle of the project was able to save roughly about $13,600 on the overall cost for hiring and firing. So we go to the next slide, and that will be our wrap up. So overall, in conclusion, we were able to set up, plan a network, as well as budget and look at budgeting constraints for the entirety of the Texas Fish and Wildlife Parks project. Thank you, and that is all that we have.